The Nernst equation allows us to calculate a cell potential, which is sometimes called an electromotive force, or EMF, whenever some of the conditions of the cell are non-standard. Here, we will address the case when the two half-cell reactions are identical, but have different solution concentrations, the so-called concentration cell. A concentration cell consists of two identical half-cells having different initial concentrations. If the two half-cells are identical, then the standard cell potential for a concentration cell is 0. Charge will flow in such a case until the concentrations are equal. So if we look at this diagram at the bottom, we have a concentration cell. We have on the left a nickel electrode and nickel 2 ion in solution. On the right we have a nickel electrode and nickel 2 in solution. The difference is that the one on the right is concentrated and the one on the left is dilute. And I've tried to show that by shading the one on the right a little more darkly than the one on the left. What's going to happen is we're going to get some charge that's flowing through this system until the concentrations are equal. Which way would charge flow? Which bar would be the anode? Which would be the cathode? And here's how we do that. We say to ourselves, well, on the left, this solution is dilute. We need more ions in this solution. And on the right, we need fewer ions in this solution. Hopefully that suggests that on the left, we're going to have oxidation taking place with some of these nickel atoms from bar A sloughing off into solution as nickel 2 ions, and on the right some of these nickel 2 ions plating out as neutral nickel atoms onto bar B. Electrons would have to flow in this case from the left to the right. Bar A would be the anode and bar B would be the cathode. And charge would continue flowing until the concentrations are equal. And I don't know if you're going to be able to see this on the video, but what's going to happen is the shading in both sides is going to become the same, and once that is complete, we have no more charge flow. We do not any longer have a cathode, we don't have an anode, we don't have a concentration cell. What's happening at bar A, as previously mentioned, is oxidation, and what's happening at bar B is reduction. If we were to add these two, because that's what we do in finding an overall reaction, we add the oxidation and we add the reduction half reactions. We can think of the nickel as canceling, the electrons as canceling, and we end up with, in essence, nickel 2 from the concentrated side turning into nickel 2 from the diluted side. In other words, in general, the reaction quotient Q is going to equal products over reactants, that is, dilute over concentrated. This will always be the case for a concentration cell. Q will be dilute over concentrated. At equilibrium, the concentrations are equal. And if the concentrations are equal, Q would equal 1. And if Q equals 1, then the log of 1 is 0, which means, if you look on the right side of the screen, about halfway up, the Nernst equation, at equilibrium, if the log of Q is 0, then this term on the right falls away to 0. We mentioned on the previous slide that E naught is always 0 for a concentration cell, and E would equal 0. Let's try an example. A concentration cell has cell A with iron 3 concentration being 2.35 molar, and cell B with iron 3 concentration being 2.25 times 10 to the negative third molar. Identify the anode and the cathode. Calculate the EMF at 37 degrees Celsius. Here's what we note. That the iron 3 concentration in cell B needs to increase. because it's much lower than the iron 3 concentration in cell A. Therefore, the iron plate in B needs to be oxidized, which means that B is going to be the anode, because that's where oxidation takes place, and bar A is going to be the cathode. Okay, so far so good. Now we need to calculate the EMF at 37 degrees Celsius. We don't need to look up anything from the reduction table for a concentration cell, because E0 is simply 0. So what we're going to have here is the value of R, which we know. The temperature in Kelvin is going to be 310. We don't want to put the Celsius temperature in there. Here we're going to move 3 moles of electrons because we're going from iron 3 to neutral iron. And for a concentration cell, Q is always dilute over concentrated. If we type all that into a calculator, we're going to get positive 0.0619 volts. Incidentally, E can never be negative for a concentration cell. It's always going to be positive. Let's summarize. A concentration cell is a setup of 2 identical half cells that have different initial solution concentrations. We determine the cell potential at any given time using the Nernst equation, with E0 always being equal to 0. For a concentration cell, the reaction quotient Q equals the dilute concentration divided by the concentrated concentration. Cell potentials E for concentration cells are typically small.